Bolts of plain undyed fabric arrive at the dyeing factory, ready for chemical transformation that will add vibrant color through synthetic dyes, recently revolutionizing the textile industry. Workers prepare brilliant aniline dye solutions in large vats, mixing chemical powders that create colors impossible to achieve with traditional natural dyes. Steam-heated dye baths receive the prepared fabric, immersing cloth in intensely colored solutions, where chemical reactions bond dye molecules permanently to textile fibers. The transformed fabric emerges from rinsing tanks displaying rich, uniform colors that demonstrate the dramatic capabilities of industrial chemical dyeing in the 1860s. Inside this steam-powered dyeing factory, plain fabric undergoes chemical transformation into colored cloth through synthetic dyes and systematic processing that defines modern textile coloration. If you could leave a like and subscribe to the channel, it would really help this project continue bringing historical industrial content. Thank you for your attention. Now back to the video. Plain woven fabric arrives daily at the dyeing factory receiving area, delivered from textile mills, where cloth production creates material ready for color application. These undyed fabrics, known as grayish goods, possess the natural cream or tan color of their base fibers, awaiting chemical treatment that will transform their appearance entirely. Workers unload fabric bolts from wagons, checking documentation that specifies fabric type, weight, and the colors or treatments requested by customers or planned for general inventory. Each bolt undergoes preliminary inspection for weaving defects or contamination that might interfere with even dye penetration or create visible flaws after coloring. The receiving warehouse accumulates substantial quantities of plain fabric organized by fiber type, as cotton, wool, linen, and silk each require different chemical treatments for successful dyeing. This systematic organization ensures proper material selection when preparing dye batches, with each fiber type processed according to its specific chemical characteristics and dye affinity. Before dyeing can commence, the plain fabric must undergo thorough scouring to remove sizing compounds, oils, and other substances applied during weaving that would prevent proper dye penetration. Workers load fabric into large scouring vats filled with heated alkaline solutions that dissolve these protective coatings and surface contamination. The scouring process involves mechanical agitation or rotation to ensure cleaning solution reaches all fabric areas, removing substances that would create uneven dye absorption or color variations. Multiple baths with progressively cleaner water rinse away dissolved impurities and chemical residues, leaving the fabric clean and receptive to dye molecules. This preparatory cleaning is essential for achieving uniform coloration, as any remaining oils or sizing would create resist areas where dye cannot penetrate properly. The scoured fabric emerges considerably cleaner than the grayish goods that entered, with natural fiber color more visible and the material's texture noticeably different after removal of sizing stiffness. Many fabrics now undergo mordanting, a chemical treatment that prepares fibers to accept and retain dye molecules through formation of chemical bonds between mordant, fiber, and dye. Workers prepare mordant solutions using metallic salts such as alum, iron, chrome, or tin, each creating different chemical conditions that affect final color characteristics. The fabric is immersed in heated mordant baths where chemical compounds penetrate fiber structure and create reactive sites for subsequent dye bonding. Different mordants can produce dramatically different colors from the same dye, with iron creating darker shades while alum produces brighter hues from identical dye solutions. This mordanting stage represents crucial chemistry that enables permanent coloration, transforming temporary dye staining into stable color that will withstand washing and light exposure. The mordanted fabric must be thoroughly rinsed before dyeing to remove excess mordant that would otherwise create uneven color or surface deposits affecting fabric appearance. The dye preparation area represents the chemical heart of the factory, where workers mix brilliant synthetic aniline dyes that revolutionized textile coloration in the 1860s. These coal tar-derived dyes produce colors of unprecedented brilliance and intensity, creating magentas, purples, greens, and blues impossible with traditional natural dyes. Workers measure dye powders carefully, according to formulas that specify exact quantities needed, to achieve desired color depth and consistency across multiple fabric batches. The dyes dissolve in heated water or alcohol water mixtures, creating intensely colored solutions that demonstrate the remarkable tinctorial power of these synthetic compounds. Chemical auxiliaries are added to improve dye solubility, control pH, or enhance fiber penetration, with each dye type requiring specific chemical conditions for optimal performance. This systematic chemical preparation ensures color consistency and reproducibility, allowing the factory to match colors accurately across different production runs or customer orders. The dye solutions are transferred to large dyeing vats, where fabric will undergo the actual coloration process. Steam-heated dye vats dominate the dyeing floor, their massive size necessary to accommodate long fabric lengths, while maintaining the solution volume and temperature required for proper dye uptake. Workers carefully load prepared fabric into these vats, ensuring the material enters evenly without tangling or creating folds that would prevent uniform dye contact. The fabric must be completely submerged in dye solution, with sufficient liquid depth to allow free movement during the dyeing process that promotes even color penetration. Steam coils or jackets heat the vats to temperatures specified for each dye type, as heat accelerates dye molecule movement and fiber swelling that enables dye penetration into the material's internal structure. Mechanical paddles or rotating drums provide agitation that circulates dye solution through the fabric and prevents settling or uneven dye distribution during the treatment period. The dyeing time varies from minutes to hours, depending on fabric type, dye characteristics, and desired color depth, with workers monitoring the process carefully to achieve specified results. If you could leave a like and subscribe, it would help keep this channel active with quality historical content. Thank you for your attention. Now continuing with the process. As dyeing progresses, chemical reactions bond dye molecules to fiber structure through various mechanisms depending on dye class and fiber type. The synthetic aniline dyes popular in the 1860s rely on ionic attractions and physical adsorption, with some developing chemical bonds under proper pH and temperature conditions. Workers periodically lift fabric samples from the dye bath to assess color development, comparing the wet material against color standards or customer specifications. This monitoring proves essential because dye uptake continues throughout the treatment period, with color depth increasing gradually until equilibrium between dye solution and fiber-bound dye is achieved. The brilliant colors made possible by synthetic dyes create dramatic visual impact even during processing, with vats displaying intense purples, magentas, blues, and greens that contrast sharply with the muted tones of natural dyes. Temperature and pH adjustments may be made during dyeing to optimize color development or correct problems detected through sample inspection. The dyed fabric undergoes systematic rinsing to remove unfixed dye remaining on fiber surfaces or trapped in the material without chemical bonding. Workers transfer the colored fabric to rinsing vats filled with clean water, where mechanical agitation or flow-through systems wash away excess dye and chemical auxiliaries. Multiple rinses with progressively cleaner water continue until the rinse water runs clear, indicating that all removable dye has been eliminated and only chemically bound color remains in the fabric. This thorough rinsing prevents color bleeding during subsequent fabric use and removes chemicals that could cause skin irritation or fabric degradation over time. The rinse water, heavily colored from removed excess dye, demonstrates the difference between dye actually bonded to fibers and the substantial quantities applied but not permanently fixed during the dyeing process. Some dye types require oxidation or chemical fixation after initial dyeing to develop their final color or improve fastness properties. Workers may expose dyed fabric to oxidizing agents or specific chemical treatments that complete dye molecule reactions or create additional bonds between dye and fiber. Steam treatment in special chambers can improve color fastness by promoting further dye penetration and bonding, while the elevated temperature and moisture facilitate final chemical reactions. These post-dyeing treatments vary significantly, depending on dye chemistry and fiber type, with each combination requiring specific procedures to achieve optimal color stability and appearance. The chemical complexity of dyeing becomes apparent through these multiple treatment stages, each contributing to the final result through specific chemical mechanisms understood increasingly well as the science of synthetic dyes develops during this period. The dyed and treated fabric moves to drying facilities where moisture removal prepares the material for final inspection and finishing. Large heated chambers or outdoor drying fields accommodate the long fabric lengths, with careful handling necessary to prevent creasing or mark creation in the still wet colored material. The drying process must proceed gradually enough to prevent uneven shrinkage or tension-induced distortion while removing moisture efficiently to maintain production flow. Workers monitor drying fabric for color uniformity and any defects that might have developed during wet processing, but only become visible as the material dries. The dried fabric displays its final color accurately for the first time, as wet fabric always appears darker and different in shade compared to the dry state that represents actual product appearance. Quality inspection becomes critical for dyed fabrics, as color accuracy and uniformity directly affect product value and customer satisfaction. Inspectors examine dried fabric under standardized lighting conditions, comparing actual color against approved samples or written specifications that define acceptable color ranges. Color matching requires trained visual assessment, as human perception of small color differences exceeds instrumental measurement capabilities available in the 1860s. Any color variations, streaks or spots receive marking and documentation, with serious defects requiring fabric downgrading or reprocessing attempts. The brilliant but sometimes unstable early synthetic dyes can produce unexpected results, making careful inspection essential for maintaining quality standards and customer relationships. Edge quality and fabric hand are also assessed, ensuring that chemical processing has not damaged fabric structure or created undesirable stiffness or texture changes. Approved dyed fabric receives final preparation for storage or shipment, with protective rolling and wrapping preventing color contamination or surface damage. Each bolt receives labeling indicating color name or number, dye lot identification, and fabric specifications that enable proper inventory management and customer order fulfillment. The warehouse accumulates diverse colored fabrics, representing the expanded palette made possible by synthetic dyes, with shades and intensities impossible before the advent of aniline chemistry. Factory records document dyeing operations meticulously, tracking dye formulations, processing parameters, and color matching information that enables consistent reproduction when additional fabric quantities are needed. This systematic documentation reflects the increasingly scientific approach to textile processing, characteristic of industrial dyeing as chemical understanding advances. The economic impact of synthetic dyes extends far beyond the dyeing factory, as color availability and cost affect fashion trends, industrial applications, and consumer access to colored goods. The brilliant colors possible with aniline dyes create new aesthetic possibilities that influence clothing design and decorative textile markets. Lower costs compared to traditional natural dyes democratize access to colored fabrics, making bright colors available to broader populations previously limited to expensive, naturally dyed materials. The dyeing industry itself transforms from craft tradition toward chemical manufacturing, requiring new expertise in synthetic chemistry and systematic process control rather than empirical knowledge of natural dye sources and traditional recipes. Inside steam-powered dyeing factories like this, chemical transformation replaces the ancient art of natural dyeing with systematic industrial processes that produce consistent colors through synthetic chemistry. The machinery and chemical systems continue operating, prepared to receive new shipments of plain fabric and repeat the coloration cycle that creates the vibrant textiles defining the era. Steam provides both mechanical power and process heat, enabling the temperature control essential for successful synthetic dye application. Workers combine traditional textile knowledge with emerging chemical understanding, operating systems that bridge craft tradition and industrial science. The transformation witnessed here represents not merely fabric coloring, but the emergence of synthetic chemistry as practical industrial technology reshaping manufacturing across numerous domains. Did you know that the first synthetic dye was accidentally discovered in 1856 and revolutionized the textile industry? If you enjoyed learning about industrial dyeing from the 1860s, please subscribe to the channel, leave a like, and comment about what surprised you most. Your support helps us continue bringing historical industrial content. Thank you for watching. See you in the next video.